Good afternoon, everyone. This is Dr. Mohit Arya from IMT College of Science and Technology, basically from IMT group of colleges. So today I will explain about the differential equations and its applications. So these are the outlines of today's educational presentation. That is, first I will talk about a brief introduction of first order and second order differential equations. Then I will tell some basic properties of the solutions of differential equations. Then I will tell about the role of Green's function in the solution of second order differential equation, which is very vast when we talk about the solution of second order differential equation. And then quantitative properties of the solutions of differential equations, and then some applications of the differential equation. So here we see the general form of second order differential equation. So this is the form of nth order differential equation. Okay, in particularly the second order differential equation can be written in the form of this. Okay, and most probably we write the second order differential equation, which is most common in nature, is that equation number 1, which is y double dash plus pxy dash plus qxy equal to rx, where p, q, r are some continuous functions of x, and here y dash denotes the first order derivative of y with respect to the variable x, and the y double dash shows the second order derivative of y with respect to x. So if rx is 0, then this equation 1 will be homogeneous, and if rx is not equal to 0, then it will be non-homogeneous differential equation. So there is a theorem which is most important. Suppose yg be the general solution of equation 2. So this is the equation 2, which is a homogeneous second order differential equation. So if yg be the general solution of equation 2, then yp is the particular solution of equation 1. The equation 1 is that. Okay. So then yg plus yb is the general solution of equation 1. Then we will say that yg plus yb and the general solution of 2 and the particular solution of 1. When we add both of them, then it is called the general solution of equation 1. The next theorem we will study, if y1 and y2 are two linearly independent solution of equation 2. Okay, the equation 2 we have studied in the previous slide, that is a homogeneous second order differential equation. Then the linear combination of y1 and y2 is also a solution for any constant c1 and c2. Okay, the third theorem says that if y1x and y2x be linearly independent solutions of the homogeneous equation 2 on the interval a b, then c1 y1x plus c2 y2x is the general solution of equation 2 on an interval a b, in the sense that every solution of 2 in this interval can be obtained from 3 by suitable choice of the arbitrary constant c1 and c2. Means if we put the different values of c1 and c2, we will get the different solutions. Okay, the solution basically depends on the arbitrary chosen value of c1 and c2. Now the next theorem says that if u1 and u2, which are the functions of x, are any two solutions of equation 2 on an interval AV, then Wronskian of these two functions u1 and u2 is either identically 0 or never 0 on AV. The next theorem says if u1x and u2x are two solutions of equation 2. Okay, so again we are taking the two solutions u1 and u2 for equation number 2 on an interval AB, then they are linearly dependent on this interval. Okay, if and only if the Wronskian is identically 0. Okay, so the theorem 4 says that if we find out the Wronskian, if the Wronskian, okay, If the round skin is identically 0, then these two solutions u1 and u2 will be linearly dependent. So we will next discuss about the second order linear boundary value problem. A second order linear boundary value problem, which is of the form that is p naught x y double dash, means second derivative of y, then p1x first derivative of y, that is y dash, plus p2x and y equal to rx. Here p0, p1, p2 and r, these all are the functions of x and are continuous in the interval ab, also satisfying the boundary conditions. The first boundary condition, that is L1y equal to alpha 1 ya plus beta 1 y dash a plus gamma 1 yb plus, that is delta 1 y dash b. The first condition we denote by the capital A, and the second condition, that is I to y, that is alpha 2 ya plus beta 2 y dash a plus gamma 2 yb plus delta 2 y dash b equals to b. So this is denoted by the b, where alpha 1, alpha 2, beta 1, beta 2, gamma 1, gamma 2 and delta 1, delta 2, a and b are given constants. Okay. If a equal to 0, means if the value of this constant is equal to 0 and b, the value of this constant is also 0, then the boundary conditions are homogeneous boundary conditions. Okay. Next we will talk about the Sturm-Liouville problems. So a classical Sturm-Liouville equation is a real second order linear differential equation, okay, which is of the form the derivative of dx dy upon dx, okay, with respect to x plus qxy equals to gamma lambda rxy. Okay, so this is the form of Sturm-Liouville equation. In the simplest of the cases, all coefficients are continuous on the finite closed interval AB. So all the coefficient must be continuous, and px has continuous derivative. Okay, in this case y is called a solution. Okay, so if it is continuously differentiable on AB and satisfies the above equation at every point in open interval AB. Okay, in addition, the unknown function y is required to satisfy boundary conditions. The function Rx is called the weight or density function. So here we consider a Sturm-Liouville equation, that is Ly plus Rxy equals to 0, where Rp is positive, P is nothing but this. Okay, so Rp is positive, R is positive, PQ and R are continuous functions on interval AB along with given PC. मतलब BC means boundary conditions. So here we consider two conditions BAY, that is alpha 1 IA plus alpha 2 PAY dash A equals to 0, B small by. So this is the second boundary condition which is at the point B, and this is the first boundary condition which is at the point A. Okay, so that is y1 yb plus beta 2 pb y dash b equals to 0. Here alpha 1 is square plus alpha 2 is square, that is not equal to 0, and beta 1 is square plus beta 2 is square is not equal to 0. The problem of finding a complex number lambda equal to mu such that boundary value problem has a non-trivial solution is called Sturm-Liouville problem, SLP. The value lambda equal to mu is called the eigenvalue, and corresponding solution y with respect to mu is called the eigen function. So SLP, there are three types of SLP. So the first SLP is that SLP is called regular. The first SLP is regular if the P is positive and R is positive in an interval AB. Second, SLP is called singular if P is positive on open interval AB and R is greater than equal to 0 on closed interval AB, and PA equal to PB, that is equal to 0. Next, SLP is called periodic if P is positive, R is positive, and PQR are continuous functions on AB along with the following boundary condition, that is YA equals to YB and the Y dash A equal to Y dash B. The most common types of SLP are regular and periodic. So next we will talk about the green function. So suppose we have a second order differential equation which is non-homogeneous in nature, that is y double dash plus pxy dash plus qxy equals to rx, where x belongs to an open interval AB. Here we see that if px, qx, rx are continuous and differentiable on AB, if two independent solutions y1 and y2x are available for the homogeneous equation Ly equals to 0, that means Rx should be 0. Ly equal to 0 means Rx should be 0. Then YH equals to C1y plus C2y, a general solution of Ly equal to 0 on AB. Now, pursuing this method of variation of parameters to get particular solution Ly equal to Rx on AB. If we substitute y equal to v1 y1 plus v2 y2 into the equation Ly equal to now in this equation we are substituting the value of y, okay, and we assume v1 dash derivative of v1, okay, y1 plus derivative of v2 y2, okay, equals to 0. Then we obtain the value of v1 and the value of v2, okay. Then yp, which is called the particular solution, that is the yp. Now, analytic and numerical methods for solution of differential equation. Most ordinary differential equation arising in real world applications cannot be solved exactly, that is right. There are lots of equations. There are like Fowler equations, like Riccati differential equations, like Abel's equation, Bertou type equations. These are the most common problems which cannot be solved easily. These ordinary differential equations can be analyzed quantitatively. However, quantitative analysis may not be able to give accurate result. A numerical method can be used to get an accurate approximate solution to a differential equation. So now we will talk about the initial value problems and binding value problems. Let us write a second order differential equation as y double dash plus fxy dash, okay. So this is a second order differential equation. Why it is a second order? Because here we can see that higher order derivative is second order higher order derivative of second order. We know that its general solution will contain two arbitrary constants and two conditions must be prescribed to determine these constants uniquely. That is, there should be provided two values of y and its derivative at one or more points. The conditions may be prescribed in two ways. Here we see that the first, all the conditions are prescribed at a single point, okay. The values of y dash, or we can say the n minus 1 at, okay, derivative are prescribed at some point x equal to a. In this case, solution is required in the domain x is greater than a, which means solution domain is open. Such problems are called initial value problems and associated conditions are called initial conditions. The second, the conditions are prescribed at two or more points, say x equal to a and x equal to b, and the solution is required in the domain AB, closed interval AB, which is bounded. These problems are called boundary value problems and associated conditions is called initial conditions. So conversion of higher order differential equations into lower order differential equation. In general, if we are having a higher order differential equation, we face such kind of problems like how can we find out the solution of that particular equation. Most generally, we study the methods to solve first and second order differential equations. In most contemporary cases, we can solve a third order differential equation. But when the order of the differential equation is increased, we may get, or mostly get, many hurdles to solve that kind of particular equations. Now here we consider second order initial value problem. Okay, here we are having two conditions at point x0, that is the initial point. Okay, introducing new variable. Here we will introduce the new variable z, which is equals to the first order derivative of y. So the given differential equation will be reduced to a system of two simultaneous equations of first order. First is what? Dy upon dx equal to z, and then dz upon dx equal to fxy y dash, with initial conditions prescribed at x equal to x0. Initial condition is given at point x0. This is the point x0 as known values of yx0, zx0. So we have seen that how a second order ordinary differential equation can be reduced in a set of first order differential equation. So here we see we are having a second order differential equation, and we reduce it into a system of equations which are both first order differential equations. The next is legendary equation. So the equation, this is the equation which is called the legendary equation, where p is a constant. Next is Chebyshev equation. The equation of form this. Okay, this kind of equation, 1 minus x square y double dash minus x y dash plus p square y equals to 0 is called the Chebyshev equation, where p is a constant, and if p equal to n, where n is integer and r is positive greater than equal to 0, then there is a polynomial solution of degree n. When these are multiplied by the suitable constant, they are called the Chebyshev polynomial. Airy's equation. The Airy's equation of type y double dash plus xy equals to 0. This equation has application in theory of diffraction, and its solution is termed as Airy's function. Hermite equation. The Hermite equation is known as y double dash minus 2xy dash plus 2py equals to 0, where p is a constant. The next is Bessel's equation, that is x square y double dash plus xy dash plus x square minus p square y equals to 0, where p is a non-negative constant. Qualitative properties of the solution. If there is a problem, then it is human tendency to seek solution of the problem, but in all cases, if not possible to find solution exactly, so knowing about the properties of solution also becomes more important. In this section, we will mainly deal with properties of the solution. Okay, so Sturm separation theorem. This is the most important theorem in the field of differential equation. We are having a homogeneous differential equation, that is equation number 4. Then the zeros of these functions are distinct and occur alternatively, in the sense that y1x vanishes exactly once between any two successive zeros of y2x, and conversely, if y1 and y2x are two linearly independent solutions of the homogeneous differential equation, then the zeros of these functions are distinct and occur alternatively, in the sense that y1x vanishes exactly once between any two successive zeros of y2x, and conversely. The next theorem we will study here: if qx is negative and if ux is a non-trivial solution of u double dash plus qx u equals to 0, then ux has at most 1 0. Qualitative properties of the solution. Next theorem says, let ux be any non-trivial solution of u double dash plus qxu equals to 0, then for all x positive, if integration 1 to infinite qx dx equal to infinitive, then ux has infinitely many zeros in the positive x-axis. Next, Sturm comparison theorem. If we are having two differential equations, one is in y, second is in z, where q and r are positive functions such that q is greater than r, then yx vanishes at least once between any two successive zeros of zx. Next, application. Now we'll talk about the applications of differential equation. So the first application is vibration in mechanical and electrical systems. So vibration occur whenever a physical system in a stable equilibrium is disturbed. You can say that. So if I talk about the vibration in mobile phone, so what are you seeing in mobile phone? When it vibrates, its physical system equilibrium disturbs and it started shaking. Okay, so you can relate that kind of situation here. For them, it is subject to the force tending to restore its equilibrium. In the present section, we will see how the situations of this kind can be lead to differential equation form. So this is the differential equation, that is d2x dt2 plus p dx dt plus qx equal to rt. Undamped simple harmonic vibration, the second application. We consider a cart of mass m attached to a nearby wall by means of a spring. The spring exerts no force when cart is at its equilibrium position, means x equal to 0. Equilibrium position means your distance is 0. If the cart is displaced by a distance x, then the spring exerts a restoring force Fs equal to minus kx, where k is a positive constant whose magnitude is measure of the stiffness of the spring by Newton's second law of motion. Okay, now here we can see that there are lots of more undamped simple harmonic vibration, that is showed in the equation number 10. Damped vibrations, which are showed in equation number 11 and equation number 12. Forced vibrations, which are showed in equation number 13 and 14. Next is your forced vibrations, which are also been showed in equation number 15. Okay. Next, Newton's law of gravitation and its motion of the planets. As we know that the planets and the satellites move in their orbit following an universal law of gravitation. That's right. Here in this section, we will see that how planetary motion can involve a differential equation and furthermore. As we know, by the universal law of gravitation, every heavenly body attracts each other with a force which is proportional to the product of both mass and inversely proportional to the square of the distance between both bodies. So, for a problem involving a moving particle in which the force acting on it always directed along the line from the particle to a fixed point, it is usually the simplest to resolve velocity, acceleration, and force into components along with and perpendicular to its line. We therefore place the fixed particle m at the origin of a polar coordinate system and express the radius vector from the origin to the moving particle m in this form. So here, if r equal to rur, where ur is the unit vector in the direction of r, it is clear that ur, that I cos theta plus j sin theta, and also that the corresponding unit vector u theta perpendicular to ur in the direction of increasing theta is given by, that is u theta equal to minus I sin theta plus j cos theta. The simple relations, okay, that are given by dur upon d theta, that is u theta, or du theta upon d theta, that is minus ur. So this is the further derivation of this particular problem. Here you can go for that. Now we will see the central force and Kepler's second law. Here we can see F is called a central force if it has no component perpendicular to r, that is, if f theta equal to 0. Under this assumption, the first of the equations 22 becomes r d2 theta upon dt2 plus 2 dr upon d theta d theta upon dt equals to 0. On multiplying tau by r, we obtain this. Okay, when we further solve it by using some algorithms, we will get a t2 minus a t1, that is equal to half h t2 minus t1. This yields Kepler's second law. The radius vector r from the sun to a planet sweeps out equal area as in equals intervals of the time. So this PPT has some references. You can read some books for further information. That is G.F. Simmons differential equations with applications and historical notes. Okay, then second is R.S. Gupta elements of numerical analysis. Macmillan publication, that is Sturm-Liouville Problem SLP. ACM, that is advanced mathematical methods, and then green function and its application, Mehndi, Dalkosh, Mohammad Dalkosh. So there are lots of writers in it, so you can use these books for the further knowledge. So this is all from my side. Thank you very much to all.